Yeah, we were talking about the properties of myocardium. We have talked about rhythmicity or automaticity. Then we have discussed about excitability of myocardium. Today we will be talking about the conductivity. So conductivity of the heart, the generation of the electrical impulse, it generates in sinus node or sinoatrial node. So this is a specialized non-contractile myocardium. And why it is non-contractile myocardium? Because the contractile protein, uh, it is almost negligible. So they don't have the contractile protein and they cannot contract. Even some of the Purkinje fiber, they have very, very few contractile myocardium, contractile protein. So they may contract, or some of the cells, they don't have the contractile protein. So this specialized cell, they play a very significant role in propagating the impulses or generating the impulses and maintain the rhythm of the heart. And because of that, generating electrical impulse and propagation, so the heart contract rhythmically, and the atria contract 1/6 of a second before ventricular contraction. And this sinus node, where the generation or the pacemaker of the heart, natural pacemaker of the heart, so they are very closely attached to the atrial muscle. As soon as the action potential generate here, the depolarizing current that moves around the atrial muscle and cause depolarization. So the atria contracts, and this atria contracts 1/6 of a second before ventricular contraction. And that is very important because uh, the ventricle needs time to fill up the ventricle before their contraction. So let's see, the velocity of the conduction in atrial muscle fiber is about 0.3 meter per second. So we know that the velocity or the movement of the depolarizing current from one cell to another cell, it is possible due to the presence of the gap junctions or intercalated discs. This gap junction from one cell, if it depolarized and it transferred to the next cell, and next cell is depolarized. So the gap junction play a very significant role for, and that is the, because of that intercalated discs of the gap junction, and this conductivity from one cell to another cell is possible. But the velocity is rapid in several small bands of atrial fiber, that is about 1 meter per second. So that small bands, for example, these are the fiber, internodal fiber, and the fiber, it directly supplies to the left atrium. So their conductivity on these small bands are very fast than the atrial muscle. So that the current which is spreading in the right atrium and equally should at the same time, almost at the same time, should reach to the left atrium. So that is possible because of the specialized small bands of atrial muscle, or that quickly transfer to the left atrium and cause similar or at the same time the contraction of the atrium. And this internodular pathway, the conductivity is very fast. It is almost around 1 meter per second. And through the internodal pathway, the AV nodes are they receive the impulse through this internodal pathway by the AV node, or AV node reach to the AV node impulse through this pathway very fast. Their impulse is moving to the AV node. So small bands, they are important because of the left atrium, supplying impulse to the left atrium or propagating impulse to the left atrium, and through the internodal pathway fiber, and it reaches to the AV node. So in AV node, it is very significant or very important. This AV node, the transmission is delayed by 0.3 second in the AV node and the penetrating portion of the AV bundle. So both together, heavy node and the penetrating portion of the heavy bundle, the transmission or impulse delayed by 0.13 second. So here there are two portions, heavy node and the penetrating portion of the heavy bundle. So in the heavy node, the current transmission is delayed by 0.9 second. And then while penetrating the heavy bundle, another 0.4 second delays the transmission. So the SN node, they generate the action potential and they move through the internodal pathway to the heavy node. It takes from SN node to heavy node, reaching to the heavy node, it takes around 0.03 second. And in the heavy node, it delays by 0.9 seconds. So if we add 0.09 second to 0.03 second, it will be around 0.12 seconds. So up to here, from SN node to at this portion, it is around 0.12 second. And from this heavy node, it is passing to the ventricles through the heavy bundle. So atrial muscle and the ventricular muscle are separated by the fibrous tissue. And this fibrous tissue barrier and along with the fibrous tissue, there are small fascicles. And because of that, the transmissions, they have to cross the transmission or delays in the penetrating portion of the heavy bundle because of the fibrous tissue that separate the atrial muscle and the ventricular. So atrial muscle, the current cannot directly comes to the ventricular muscle. So this fibrous tissue, along with the fibrous tissue, the small fascicles, they also run along with the fibrous tissue. And this barrier, because of this barrier and that transmission, they have to pass cross this area. So it delays by 0.04 second, and then it reaches to the bundle branches, left and right. So almost it will take, if we add 0.04 second to 0.12 second, then almost 0.16 second it's required to reach to the bundle branches. As soon as they reach to the bundle branches, it goes to the Purkinje fiber, and the transmission is very fastest. Purkinje fiber transmission is very fast. So why the heavy nodes, that delays the transmission? And it is important to delay the transmission because the atria have to contract before the ventricle. So that delays is necessary. And by almost more than 0.1 second. So this heavy bundle, why it is delays? Because it has a less gap junctions or diminished gap junction. So when there is less gap junction, the transmission of the positive current to one cell to another cell delays. And because of that, the resistance to conduction of excitatory ions. So because of the less gap junction, so there will be resistance to conduction of excitatory ions. So the excitatory ion moving from one cell to another cells are delays or slows down. And because of that, next cells are not stimulated or slowly stimulated. And that is important because the ventricle have to contract after the atrial contraction. And Purkinje fiber, it is the fastest conduction. The velocity is around 1.5 to 4 meter per second, almost 6 times that in the ventricular muscle, and 150 times than that in some heavy nodal fibers. And the transmission is instantaneous, very fast. Immediately, they distribute the current throughout the ventricle. The bundle branch to the termination of Purkinje fiber, total time is around 0.03 second. So here, as soon as the current comes to the heavy bundle branches, after crossing the heavy and penetrating portion of the heavy bundle, then the transmission is very fast. It takes almost around 0.03 second to reach to the end portion of the Purkinje fiber. So as soon as they cross the penetrating portion of heavy bundle, the transmission is very fast. Now, these are the several point, fraction of the second where the transmission takes place. So here 0.6 second, then 7, then almost 0.9 second to the end portion of the Purkinje fiber. So 0.01 second minus 0.19 second. It is almost 0.03 second. So it is a very fast impulse is moving to all over the ventricle through the Purkinje fiber. So when we talk about the ventricular muscle, so the Purkinje fiber, they distribute the current to the ventricular muscle, and in the ventricular muscle, the current flow from one ventricular cell to the another ventricular cell through the gap junction. So the transmission in the ventricular muscle is slower than the Purkinje fiber. It is around 0.3 to 0.5 meter per second. It is almost 1/6 of that in the Purkinje fiber. Transmission from the endocardial surface to the epicardial surface of the ventricle requires 0.03 second. Here we have to understand this inner layer is the endocardium, and then we have the myocardium. Myocardium have the properties what we are talking about, the having the gap junction and the conductivity. Then over the myocardium we have another layer, that is epicardium. So from ventricular muscle, that is means myocardium, between the endocardium and the epicardium. And so from endocardial surface, endocardium from to the epicardium of the ventricular muscle, all over the ventricular muscle, at the end portion of the ventricular muscle, the depolarizing current to reach to the end of the ventricular muscle after supplying by the Purkinje fiber, it takes around 0.03 second. So impulses, so from between the ventricular muscle from endocardium to the epicardial of the ventricular muscle requires 0.03 second. And from epibundle, after penetrating the epibundle branch portion, then to the Purkinje, termination of the Purkinje fiber, it takes around 0.03 second. And from ventricle 1 and 1 surface, endocardial surface to the epicardial surface, it takes around 0.03 second. Total from epibundle, penetrating portion of the epibundle to all over the ventricular muscle, including the Purkinje as well as ventricular muscle, it takes around 0.06 second. And then the ventricle contracts when it whole over the ventricle transmission takes place. So that is how the transmission in the heart takes place. From SA node, it reached to the AV node by 0.03 second, and from AV node it delays by almost 0.1, more than 0.1 second, and then when it reached to the cross the penetrating portion of the AV bundle branch, then Purkinje fiber very fast, 0.03 second, and from ventricular muscle from one endocardial surface to the epicardial surface, it takes around 0.03 second. But here the current will not go away from the heart. It is from the ventricle and the atrium. So the impulse is moving through this conducting system from SA node, AV node, and then from SA node directly to the left atrium, then Purkinje fiber, and then all over the ventricle, and then the ventricle responds by contracting. That is about the conductivity of the conduction or propagation of the conduction of heart muscle.